OK OK 好，and so I switched to the first part because actually the second part has not been fully finished yet. Of 1 week ago, I thought we can finish it in a week, but actually it took longer than I thought. So I have to slightly cut the second part. So this is the two part of the talk. And, I'll talk about non-Hermitian physics and actually, there are several important features in non-Hermitian systems. And one of the features is that the operators or the metrics, the non-Hermitian metrics, usually have complex eigenvalues. So, and in this talk, I will consider adding disorders, adding some non-Hermitian disorders which has clear physical meanings. And we found that the transport behavior follows some universal laws, which I will tell you. And in the second part, the motivation is not in the eigenvalues, but in the eigenstates. The eigenstate of the non-Hermitian operator has a interesting generic feature called non-Hermitian skin effect. And we consider many body physics that involve the non-Hermitian skin effect and find that this feature dramatically reshape the steady state of the certain open quantum system. Here, non-reciprocity means that it usually refers to some asymmetry in the hopping. For example, the hopping from left to right is different from that of the right to the left. So this is called non-reciprocity. And so there's a lot of physical systems which involve non-Hermitian operators. And for example, in photonic system, in cold atom systems, which is an open quantum system, and in quantum optics, and in cavities, or even in the non-equilibrium statistical mechanics. And there is a lot of physical origin of non-hermiticity. And this is a table from this very long review articles. So this is an incomplete list of some origin of non-hermiticity. For example, there can be gain and loss in certain classical or quantum open systems. And in the open quantum system, there can also be dissipations. And in fact, in the first part, in the part A, we will consider gain and loss. And in the second part, the non-hermiticity comes from dissipation. So the first part will be about transport in disordered non-Hermitian systems. We found some universal transport behavior. This work is done mostly by these two guys, two postdoctors in our institute, Li Bo and Chen Chuang. So the story starts from a very old paper, which everybody here knows. It's many years ago, Anderson found that in some disordered systems, the wave functions are localized by the disorder. So the general picture is that in a perfect periodic lattice, the eigenstates are Bloch waves, which is extended in the entire system. But if you add some disorder to the material, in the presence of weak disorder, the Bloch wave is generally distorted to some, maybe still extended, but not the ideal Bloch waves with the ideal periodicity. And when the disorder is become very strong. The eigenstate become completely localized, which is very different from the Bloch waves. So in terms of the Hamiltonian, we have this kind of hopping with some on-site potential V, which follows some distribution, for example, Gaussian or some other distributions. And here we have to emphasize that, in fact, there are twofold meanings of Anderson localization. Usually we just say Anderson localization, but the meaning is actually twofold. The first meaning is that the eigenstates are localized. And the second meaning is that when the eigenstates are localized, the transport is prohibited. So when the eigenstates are fully localized, then there is no transport. If we input some wave packet in the system, then the wave is always localized there. So, but in Hermitian systems, this twofold meanings is often not emphasized because these two are actually equivalent whenever the eigenstate becomes localized. In electron system in the Fermi level, then the electron cannot transport, right? Now, what we will consider is a non-Hermitian version of this Anderson model. So in the original the Anderson model of the disorder, we have a randomly distributed potential. But here we consider some randomly distributed imaginary potential. So this actually has very simple physical meaning. If we describe some waves, this imaginary part describes the gain and the loss. And this model means that the gain and loss is random. So this is physically very simple. So what we ask is the fate of the Anderson localization in this non-Hermitian version of the model. Simple. So this is inspired by some recent experiment in this paper a few years ago. So they did this in optical systems. They construct something that almost exactly simulated the Hamiltonian in the previous slide. So in the Hermitian case, with this is consistent with the original Anderson prediction, which is well known. So the eigenstates are localized, and there is no transport. But in the non-Hermitian case, they find something more interesting. So they find that by the calculation, they find that the eigenstates are still localized when you have an imaginary disorder. But now the transport is not prohibited. Actually, there is a transport of waves. If we have some wave packet at some position, then actually it's evolved away from the original site. They will gradually the distance from the wave center to the original site actually grow with time. So this twofold meaning of Anderson localization becomes different in the Hermitian case. We need to distinguish this twofold meaning.
You find some sort of electric field or something similar to it?
Actually, even simpler than that. Maybe you can consider even a classical wave system with gain and loss. The wave, you start from some wave here and it evolve according to this equation, and then you measure the expectation value of that. Yeah, the wave evolve according to the Hamiltonian. The Hamiltonian contains the gain and loss, and evolve according to this Hamiltonian. But it can evolve in every directions, but you can average the distance. So this is a one-dimensional case. We can do some numerical simulation. So here, this is a real disorder case, which is very familiar to all of us. So initially, the wave expands a little bit, but then it becomes confined to a certain distance, which is actually just the localization length. This is very familiar. But in the non-Hermitian case with random gain and loss, the wave stays here for a while, then it moves to some nearby place and stay for a while, and then it appears to jump from here to here. So the wave center gradually moves in a somewhat jumping way. So let's also mention that this is a normalized wave function. So actually this does not disappear here, but it disappears just means that the strength here is larger than here.
So every time state is normalized.
Yeah, it's you can evolve it according to this Hamiltonian. Then you normalize to, for example, to take the integral of the wave function weight to be 1. Yeah. But this is also nature from the experimental point of view, because you can see the bright location. If you have an electromagnetic wave, then where the location of the wave center is very bright, right? Experimentally, this is very easy to detect. We care about the relative field strength. So in this way, the wave appears to jump from here to here. So it can still move, not localized. And the physical picture is actually not very difficult to understand. There is some intuitive argument that tells that this behavior is possible. We can do some very simple math. So we have an initial wave, right? Initial wave packet. We can expand the initial wave in terms of the eigenstates. So this eigenstate, psi x, which is labeled by the center of the eigenstates. This psi x means eigenstate localized near x. So when you expand the wave in terms of the eigenstate, the coefficient will decrease with the distance, right? So if you have some, for example, see the black lines, you will have some, each black peak is can be viewed as the eigenstate. Then if the initial wave is near this location, then the coefficient, the contribution from the eigenstate far from this wave center will be exponentially small, right? So but after time evolution, this coefficient require some additional factor, which we denote this coefficient as A of t. So this A of t is the original factor multiplied by this time factor, which is e to minus I e. And so this is very simple, because this simple factor comes from the eigenstate, right? Because this psi x is the eigenstate, so the time evolution only give us this exponential factor. So now there is some difference between Hermitian and non-Hermitian case. If you take the modulus of this factor, then in the Hermitian case, this is a fifth, this is just a fifth factor which does not contribute. But in the non-Hermitian case, this factor becomes more important because it can have the imaginary part, which means that it can increase or decrease this factor dramatically. If this is bigger than 0, then it causes increase, right? Otherwise, it decreases this factor. So here is a picture of this evolution. So initially, the initial wave function at time 0 can be expanded in terms of in this eigenstates, and the coefficient becomes smaller at a larger distance, which is illustrated by this decrease in height. So, but after some, this is black line, this is black curve. But after some time evolution, and each eigenstate gains some factors here. Then some eigenstate with a larger time factor plays more important role, right? So if this eigenstate has a larger imaginary part than the center one, then as time grows, it will grow quicker than this one. And for example, if this imaginary part is negative, then it even decreases. So this eigenstate becomes more dominant than this center one. So after some time, it seems that the eigenstate, the wave moves from here to here. This explains the basic picture of the jumping motion of the wave. So the picture is quite simple. And with this preliminary understanding, we ask whether there can be some universal behavior in this non-Hermitian transport. So we have seen that the mechanism of transport is very different from the Hermitian case. It's deeply related to the complex valued of the non-Hermitian operator. So we ask whether this different mechanism can generate different behaviors. So we did some numerical calculations, which is shown here. So we indeed see some universal behaviors. For example, at the initial stage, the distance from this means average distance of the wave center from the initial site. So we do a lot of calculation on different sampling. So then we average over the different samples. So the average distance follows some very simple rule. So at the initial stage, the expectation of the distance from the original site follow this square root law. But when the time becomes larger, then it crosses over to some other. This is 2/3 law. So not only we have some scaling law, but it's even richer than what we expected. So we even have crossover between different scaling laws. So here, so when the time is very large, there seems to be some deviation from the this two-thirds law, which is just due to the small size of our calculation. So we can see that these three colors come from different sides. So when the size is larger than this, this red curve will be consistent with this line for a longer time. So which means that in the infinite size limit, this two-thirds law will be valid to the infinite time. So this is some universal scaling law coming from numerical calculation. So with this, we would like to understand what's the origin of this scaling law. So how to simply understand why this scaling law can be seen here. So we get some insight from the Morton's variable range hopping, which is a textbook result in kinetic matter physics. So experimentally, it was found that at a very low temperature and in disordered systems, this conductance follows some very simple law, which is in 3 dimensions, when the D is 3, then we have this minus quarter law, right? Which is the experimental curve suggests. So Mort gave a theory for this effect. So physically, it was understood that in disordered systems, electron, although the eigenstates are localized, the electron can still find some phonons, some thermally excited phonon to assist them to transit from some site to another site, which is quite far from the initial site. But Mort showed that this in this picture, he can indeed got some scaling law. Let's review how did he obtain this very simple scaling law. In fact, the conductance is proportional to the how easy the electron can hop from a side to some other side. So this hopping depends on 2 factors. So, and one factor is come from the wave function overlap. When electron hopped from a certain eigenstate to the other eigenstate, contribute this exponential factor. The farther away the 2 eigenstates, the smaller the probability. But here there is another factor, which is the phonon contribution. So the electron need to find some phonon with energy delta to assist its hopping. But finding this phonon is given by this exponential factor. So this factor, the first factor, of course, prefers hopping at a smaller distance, right? Because this would benefit from the larger wave function overlap. But for the second factor, it prefers larger hopping distance because at larger distance, the density of state will become the density, the level spacing will becomes shorter, becomes narrow, right? So the level spacing will become smaller at a larger distance r. So at a larger distance, the electron can find, it's easier for the electron to find phonons to assist the hopping. So this actually it's inverse proportional to the volume. So this gives us this factor, which is contains two contributions. One proportional to the R, but the other inversely proportional to the R to D. So there is a balance between these two factors. And we can optimize the hopping rate between these two factors. We just take the derivative with respect to the distance R. So we get the optimal hopping distance is this. And the probability, the exponential probability, when we insert this distance here, give us this. This is Morton's law, and in the 3 dimension, which is consistent with the experiment. So now come back to the non-Hermitian transport problem. We see that we have a very similar situation. What we want to maximize is this. This is the contribution of the different eigenstates. The coefficient depends on two exponential factor. The first one from the wave function overlap, and the second one not from the temperature, but from the contribution, the time factor from the time evolution. So here, actually the time plays the role of temperature in the Morton's problem. So we would like to balance between these two factors. So the situation is very similar to the Morton's case. So in the Morton's problem, he got some universal conductance behavior. So of course, we want to see whether this similar argument can apply to this case. Indeed, it is. We can do similar calculations, very simple. So we would like to maximize this rate. Then we take the derivative of this exponent with respect to x to the hopping distance, not the hopping, but here it's not the hopping, but the distance from the wave center to the original site. So in a larger volume, it's easier to find some eigenstate with larger imaginary part, right? So the wave will want to search for larger imaginary part of eigenstates, which increase the coefficient. But for the larger distance, the wave function overlap will be smaller. So we have to balance these two factors. So this gives us this equation. The optimization gives us this very simple equation, similar to Morton's case. So here, this is of course different from Morton's problem. So this is the imaginary part of the eigenstate. So the probability of finding a bigger imaginary part of eigenstate should be at the order of unity, which means that we can find some eigenstate in this volume. So from this, the bottom line is that we have some the lambda is a function of x. So this is similar to the more to the case that the level spacing is a function of the x. Level spacing is a function of r, which is just the equivalent to x here. So with this, we can input this function here, and we can get x, the spreading distance as a function of t. The idea is indeed quite similar to Morton's problem. And so this is a sample calculation. So if the density of state is Gaussian, then the probability of finding some eigenstates with a larger imaginary part is given by this p. And we can do some expansion here. And we got this lambda as a function of x, and with this equation of optimization, we have this very simple behavior, which is sub-diffuse, sub-ballistic. So in the Gaussian case, if there is no this factor, without this factor, it's just ballistic. But in fact, it has this factor. So for other kind of density of state, for example, for the constant density of state, we have this simple power law scaling. And for the linear density of state, which is given by this one, we have this kind of scaling with a different exponent. So this theory is consistent with many numerical simulations. For example, for the Gaussian distribution, the numerical simulation also is indeed consistent with this prediction. And now, finally, we come back to the first numerical simulation I showed you. So this is a crossover from the square root law to the 2/3 law. So you may ask that what I told you is some universal behavior, but why is there is some crossover from different scaling law? So the reason is actually quite simple. According to the picture I have outlined, so the wave want to search for larger and larger imaginary part of the eigenenergy, right? So it will the dominant weight actually moves from the right to the right. So the eigenstate with larger imaginary part will gradually dominate the coefficient. So for infinite systems, there is no largest imaginary part. So the wave can always in pursuit of larger and larger imaginary part. So it goes to the right edge of the density of state. So at the initial stage, the density of state appears to be uniform. So according to our theory, this gives us this square root law, according to the calculation. But for a larger density of state, for a larger time, the weight is dominated by the right edge of density state. So usually we do not have a sharp drop, right? It is some linear, it looks linear at the edge. So the behavior should be predicted by the linear case, right? So for the linear density state, we have a different behavior of the spreading distance. This is why we have crossover at the initial stage to the a different exponent at the later stage. It's because the dominant eigenstate comes from the right edge of the in the figure of density of state. So this gives us the crossover. So this is the first part of my talk. Okay.
So I guess in real physical system, for a photonic system, I guess probably you cannot, even if the imaginary part is, I guess, a positive, it cannot grow forever. So
yeah, this prediction is in the linear regime. So in fact, in the if the field strength is too strong, then you always will have nonlinear effect, which will suppress the growth. But in this case, so if you have loss, then this will always be valid. So
if it's just a loss, like for example, the imaginary part is like upper bounded by 0 or something, or any lower bounded by 0.
So if you
like it's getting exponentially smaller. So although there will be a brightest part.
Yeah. Yes. Yeah, it will be harder to detect, but if your measurement is very precise, then you can still see this, right? But so it's within the linear regime, and when the field strength is measurable, then this is somewhat restricted to this regime. Otherwise, we cannot have very simple theory. It's much more complicated. So I think another question.
What's the effect of this still state? I mean, let's start from the edge region, let's start from some line edge actually E and then extends to
So this is the density state of actually for the infinite size, it looks just like this. Yinfei has a question, right? Oh, so I think your question is related to the previous one. So the second part is something that what I said takes longer time than I expected. So I will be quite brief in this part. So about how long reciprocity shapes the steady state of open quantum systems. So this is the outline for the second part. So it involves some concept called non-Hermitian skin effect, and then we'll talk about its effect on the steady state. So so one of the interesting feature of non-Hermitian Hamiltonian is that if you calculate the spectrum under different boundary conditions, it looks very different. For example, this is open boundary condition, and this is a periodic boundary condition. So under the periodic boundary condition for this Hamiltonian, you have this kind of spectrum. But under open boundary condition, it looks very different. So they are different even in the thermodynamic limit. And so a side remark, this actually these two kind of boundary conditions also important in the ancient time. So this kind of stone, so in the ancient China, if a friend of you send you this as a present, so it means that he or she don't want to be friend of you anymore. So this means that want to break the relationship with you. So if they send you this one, that means that you are still a friend. So the difference is in fact very important. So this the reason of this condition is a non-Hermitian skin effect. It means that if you have open boundary conditions, the eigenstates are actually exponentially localized near the boundary. It's not a Bloch wave. It's some exponentially localized wave close to the edge. So which is why we call it skin effect. Actually, I coined this terminology. So with this strange behavior, many phenomena should be reconsidered in this framework. So one of the concepts which I think I don't have much time to go into details, but the idea is that the concept of the Brownian zone should be revised according to this phenomena. So in the if we write down the wave function in terms of Bloch wave, it means that the modulus of the phase factor e to ik is equal to 1, right? So this is give us a unit circle, which is a standard Brownian zone. But when we have this skin mode of the non-Hermitian skin effect, then it means that the modulus of beta should not be 1. So it means that we should generalize the concept of the Brownian zone to some more generic curves. So there is some equation that give us this generalized Brownian zone. But I will not show it here. So this kind of theory has many applications mostly in the dynamic aspect of the non-Hermitian system. For example, we perturb certain systems, certain non-Hermitian systems. For example, we would like to calculate the response of a non-Hermitian system with gain and loss. Then the response is given by some Green's function. And sometimes this Green's function is not symmetric between the exchange of the indices. This means a phenomena called non-Hermitian problems because okay, thank you. So this is indeed a non-Hermitian system or open system with loss, right? So the power gradually lost. And okay, so it's okay. I'm not sure whether okay. So to calculate the grid function of the non-Hermitian Hamiltonian, actually we need this theoretical framework. We should do integration of over the generalized Brownian zone instead of the standard Brownian zone. I will omit the details of this, but I just mentioned that most of the studies are focused on the dynamic features, which means that it's not about the steady state itself, but about some response of the steady state. Here, I would like to study the effect of the skin effect on the steady state itself. First of all, let's mention that this non-Hermitian physics and non-Hermitian skin effect is actually relevant in open quantum systems. Okay. So the not only relevant, the non-Hermitian physics is not only relevant to the classical wave system, it is also relevant to the open quantum systems. At least in the Markovian approximations, in this case, we focus on the density matrix, which evolved according to the Lindblad master equation. The density, if we view the density matrix as a vector, or obviously we vectorize this density of state, then the time evolution of this density matrix takes the form of the Schrödinger equation, but the operator here is not Hermitian. It's not Hermitian. So the many features of non-Hermitian physics is also seen here. For example, the eigenvalues becomes complex, right? So here we consider a concrete model, which involves some non-reciprocity. So the hopping contains an I factor here. So by itself, it looks not quite non-reciprocal because this is the Hamiltonian part, which looks Hermitian. But together with these dissipations, it will generate some non-reciprocity in the physics process. So we have some Hamiltonian, which describe the hopping of some particles in the lattice. We also have some two-body term, which coherently generate two bosons or destroy two bosons. This is the Hamiltonian part. And we also have a single particle gain and a two-body loss, which is important for the system to be stable. So when there are too many bosons here, it will go away from the system. We also have this dissipator which couples different sites. So this is give us some nonlinear effect in the open quantum system. So first of all, we would like to study the problem from the mean field viewpoint. So we consider the expectation value of the boson operator, which we still called B of J for simplicity. We do not use this average, the notation of average. So it is described by this effective Hamiltonian. First of all, we would like to start from the vacuum state with all Bj equal to 0. Then we consider the fluctuation around this vacuum state to see whether the vacuum is stable. So if it is unstable, then we go ahead to see what's the fate of this vacuum state. This is a strategy. So this fluctuation is described by this. Sorry, before the talk, a few minutes before the talk, I noticed that there is a typo here. This is actually for a different spatial dimension. So in one dimension, this is 2, but this is correct. So we have this non-Hermitian effective Hamiltonian with a non-reciprocal hopping. So, so for the system to be stable, we don't want to have positive real part. So because in the open quantum system case, the notation is often opposite from of real and imaginary part is often opposite. Here the real part describe the dissipation actually. So if the real part is positive, then it means some instability. So here we see that this is the spectrum of the periodic boundary condition, which is always unstable. So there is always positive real part of some mode. But for the open boundary conditions, the vacuum can be stable or unstable according to the parameter values. For this parameter, the real part is negative, so we have a stable vacuum. But in some other case, we can have unstable vacuum. The interesting feature is that the non-reciprocity actually plays important role only under open boundary conditions. So we can see from these equations, for the periodic boundary condition, the non-reciprocal term, the J term, actually cancel out because let's look at this. So if we take a uniform value of B here, then we can see that these two terms actually cancel each other, right? So if we start from a periodic boundary condition with a uniform initial state, then actually these two, the non-reciprocal term does not play an important role. So the instability actually leads to a uniform steady state, whose value actually does not depend on this J. But in the open boundary condition, there is no cancellation at the edge. In the bulk, if we start from a uniform initial state, there will still be cancellation, but at the edge, there's no cancellation, right? Because there is at the left edge, there is no left label, so the cancellation is incomplete. So in this case, maybe we can expect something more interesting than the periodic boundary condition. Indeed, we see some interesting phase generated by this non-reciprocity. So we can evolve so one of the phase which is interesting is this one. This is the traveling wave case. If we start from the uniform initial state, then since the non-reciprocity enters at the edge, as I mentioned in the last slide, and it will from some numerical calculation, we can see that the effect will gradually go into then after some time, it will look like this. So there is some traveling wave entering from the edge into the bulk. So after a sufficiently long time, then the entire steady state will be reshaped by this non-reciprocal term. So, but under periodic boundary condition, this mechanism is impossible. So the non-reciprocity seems to be muted in the PBC case, but becomes effective in the OBC case. So this is since actually I'm running out of time, I will not explain. This is actually a fancier way to plot the same figure. So actually we can, of course, we can worry that the mean field theory is invalid in one dimension. So we did a lot of calculation in 2 dimensions, which is which is quite consistent with the expectation of the picture I just outlined, but it takes longer time to get in the data. So I will not show the incomplete data here. So let's go to the final slide, the conclusion. So the talk is divided into two parts. In the first part, I talk about non-Hermitian transport, which include the twofold meaning of the Anderson localization in non-Hermitian systems, the spectral localization of eigenstate and the dynamic behavior of the wave transport, which is the same thing in the Hermitian case, but different in the non-Hermitian case. Talk about the universal transport behavior, which whose picture is very close to Mort's variable range hopping, but with the time playing the role of the temperature of Mort. So then, of course, with this, we would like to investigate to see whether there are some more universal behaviors generated by non-hermiticity in, for example, in transport behavior. In the part B, we talk about the role of the non-Hermitian skin effect in generating or shaping steady state of open boundary open quantum systems. So the role of non-usability strongly depends on the boundary condition. It seems that it is muted under the periodic boundary condition, but toned down under OBC. So, of course, in the open quantum systems and which involves many body physics and other effects such as non-Hermitian skin effect, we still need some organizing principle which go beyond to this study case by case. So thank you very much.
Yeah, so thank you for the very nice talk. I wonder if you could comment on how much of this is dependent on the existence of, periodic or open boundary conditions, and how much of it is the non-reciprocity. So, for example, if you had directed hopping, there is a stronger hopping in one direction versus another. Do you think some of the same effects would hold, or in a periodic system where you have hopping in one direction that's stronger? What do you think would occur in that situation?
Yeah, actually, in our model, effectively, the hopping is stronger towards the right.
I see.
But here, if you have a uniform state, then this term actually does not contribute, because this J term cancels. For example, if you take all this to be equal to some value B0, then this term actually cancels. So the non-reciprocity actually does not play any role in this PBC case.
Yeah,
but in OBC case, this cancellation is seen in the bulk, but not at the edge. So the non-reciprocity will work at the edge. But from the edge, it can gradually affect the bulk. Then after a very long time, it will affect the entire bulk.
Yeah,
that's a question.
Thanks.
So you mentioned that this form is obtained from Lindbladian.
Yeah.
Can you go to the Lindbladian again?
Yeah, this is the Lindbladian.
I see. And when you consider the evolution of B, did you focus on like a no jump condition or?
Not of the no jump condition. So if you focus on the no jump condition, then it cannot be done experimentally.
Right.
Because you need post-selection. So what we did is much better than that. We actually consider the full evaluation.
So so what you examined is really the Lindbladian steady state.
Yes, yeah. We do the calculation based on some uh what I show is mean field calculation, but we also do some more advanced calculation from the truncated regulars or some advanced technique, which is start from the full Lewisian.
I see. Because I guess it's very hard to simulate large system size for especially when you have a Lewisian. I was
Yes.
wondering whether you could compare with.
It's not actually not entirely exact because I just mentioned the exact diagonalization is possible only for a small size, but there is some other method which is generally quite, I think it can be trusted. Which has been tested in some other systems for like the truncated Wiggler. So it's not exact, but it gives us some trustable result, which is also consistent with our intuition in this case. So I think it's not bad.
But finally, have you examined the Lindbladian gap for this situation?
The
As a function
Lindbladian,
of maybe K and J, or whether depending on the open or periodic boundary condition.
um, I think we didn't do the Lindbladian gap calculation. I think uh, it's, yes, because we focus on the steady state. So for the Lewisian gap, usually it's used for detect the excitation on the steady state. Here we care more about what the steady state is, so we didn't calculate the Lewisian gap. But I think we can calculate it. For example, even the scaling of the gap with the system size. And as I mentioned, this project is actually not finished yet.
Okay.
So there's quite a few things to calculate.
Would you expect the so I mean Lindblad game is basically 1 over the mixing time, and do you think mixing time would depend on the boundary condition?
It's depends on what kind of way you do the experiment. If we do some experiment very deep in the block, then actually the relaxation time does not depend on the boundary condition. But if the measurement is close to the edge, then it will depend on the. So that's actually this is a good question because in many cases people say that the effect of the skin effect is just probably can be seen only in the near the boundary, but deep in the block, you cannot feel the effect of edge. But in the case of steady state, so the skin effect indeed has a very strong effect on the systems after a long time. Because the skin effect reshape the steady state, then not only the physics near the edge is affected, but the physics of the entire system is changed.
Okay, let's thanks the speaker.
Yeah, thank you.